Okay, let's continue our derivation for the plane wave equation and the general solution for wave equation as well as the specific solution. So in Tuesday, we have derived a general solution for MET for plane wave. And equation 3.78 is the general solution for one-dimensional propagating electromagnetic wave, the electrical field intensity expression, which comprise two components, AF and BG. And the difference between function f and function g is that AF function f represents a component that is propagated toward the positive z direction, while function g stands for the solution for the components propagating to the minus z direction. So the difference can be seen from the composition of the function parameter. That is, for function f, it's t minus z times square root of mu times epsilon, and for function g, it's t plus z times square root of mu times epsilon. So the difference in the t minus z and the t plus z contributes to the difference, so that the function f represents the components propagating toward the positive z direction, and g is for the minus z direction. A and B are constants that specify the weighting of function f and function g, which can be determined later according to the boundary condition and source function, so that we can derive the ratio of A and G for the two propagating components. And to be noted is that for this equation, this is only valid for a y-dimensional case. That is, the wave is propagating along the z direction. It's going to either positive or negative z direction. And in this slide, we derived the expression, the general expression for the magnetic field H, which can be done using this relationship. So to derive H, we need to first perform a partial differentiation on Ex with respect to z, then perform integration on with respect to t, time integration, so that we get equation 3.79. It's in the form of AF minus BG. So to be noticed that the difference is there is a minus sign about the G component. So it's AF minus BG divided by square root of mu over epsilon 0. And this is the so-called intrinsic impedance, which will be discussed a little bit later today. So the E and H field were in the form of AF plus BG, and H is in the form of 1 over eta times AF minus BG. The generation of the minus sign is due to the formulation of the parameter, because one of the parameter is t minus z times the square root of mu times epsilon. So when you perform the differentiation, here comes a minus sign over there. All right, and this slide shows an example of the f function, which is in general not the wave propagating function that we well, this is just an example for the f function, but it's for propagating waves is in general not in this form 啊，所以这一个抛物线的那个只是一个例子啊，真实的传播的电磁波不会长这个样子了哈。那这一个例子的重点在于它的参数是 t 减 z 乘上 μ epsilon 开根号啊，只是要特别去强调这一个参数的效果啊。So the example of function is a parabolic in parabolic shape. So because it's a parabolic curve, so you can see that it reaches minimum at this point, which is satisfied for t equal to 0 and z equal to 0. So as the time increases, say that t equals to square root of mu times epsilon, then the minimum shall move to position z equal to 1. So this shows an example that as the time progresses, this parabolic curve will move to the right. So it stands for a wave that is going to the positive z direction. Therefore, if we want to make an example for the g function, we can simply replace t minus z as t plus z, so that the parabolic curve shall move to the left instead for the g function. And as to the parameter for the function, that is t minus or plus z times square root of mu sub 0 epsilon, you can see that the minimum is satisfied when the parameter equals to 0. This is the minimum for the parabolic curve. So what happens if we do a differentiation over the parameter? So if we if we take a differentiation over the parameter, what we have, we will end up with dt minus plus square root of mu 0 epsilon 0 dz. And if this is set to 0, we end up with dz over dt equals to plus and minus 1 over square root of mu sub 0 epsilon sub 0. What is the physical significance of this parameter? dz over dt is what? Is the movement of position in a specific time interval. So therefore, the physical significance of dz over dt is the velocity v. Then, to the right-hand side of the equation equal mark, this stands for the velocity of the wave. And it can be represented with 1 over square root of mu times epsilon. So if the propagating medium, if the environment is vacuum, is free space, then mu sub 0 is 4 pi times 10 to the minus 7, and epsilon sub 0 is 8.854 times 10 to the minus 12. And the inverse of the square root of mu times epsilon is 3 times 10 to the 8th. That is the that is the velocity of light, the velocity of electromagnetic wave in free space. Okay? So the velocity of light, the velocity of electromagnetic wave is determined by the propagating medium. In particular, the permittivity and permeability of the propagating medium. So for free space, the speed of light is around 3 times 10 to the 8th. As you already know it. All right, so the significance of 1 over square root of mu times epsilon is what? Is the velocity of the propagating wave, including the waveform. So F stands for the components propagating toward the positive z direction, and G stands for the components goes to the minus z direction. And here is a more detailed derivation for the velocity of electromagnetic wave. It uses the concept that, say, if the original time and space is t1 and z1, then with a small increment in time and a small increment in space, that is t1 plus delta t and z1 plus delta z, that the wave shall remain in the same shape. The only difference is the waveform is shifted to the right, and by dividing the position difference over the time difference, we can get the velocity of the wave. So as you can see here, if the parameter is the same, if the parameter in the function is the same, then the function value should remain the same, which means that the waveform should remain the same shape. The only difference is its location, its position is shifted to either positive z or negative z direction. So to satisfy this requirement, the parameter should be the same. So t1 minus z1 times square root of blah blah equals to t1 plus delta t minus z1 plus delta z times the square root of this. Then you can simplify this equation as delta z equals to delta t over square root of mu times epsilon. So with a shift of the variable, it becomes delta z over delta t, that is, the velocity of the wave equals to 1 over square root of mu times epsilon. So substitute with the permeability and permittivity of free space, you will end up with 3 times 10 to the 8th. And the same velocity can be derived for the function g. The only difference is the delta z over delta t result is minus 3 times 10 to the 8th, which where the minus sign stands for the wave propagating direction is toward the minus z direction. So we can say that based on the formulation of the function parameter, we can tell that this wave is going to either positive or negative z direction. And the other thing that I would like to discuss is the significance for eta. Eta, well, of course, Greek letter is then in electromagnetics. Eta usually refers to the intrinsic impedance of free space for eta sub-zero. Sub-zero. So if you see sub-zero, it means the property in free space. So eta stands for the intrinsic impedance for free space. Intrinsic impedance is translated as 本质阻抗 in memory. In electromagnetics, there are 2 most fundamental impedances that you may come up with. One is the intrinsic impedance, the other is the so-called characteristic impedance. Characteristic impedance 叫特性阻抗，或有人叫特征阻抗了，特性阻抗了哈。Characteristic impedance， 然后再来是本质阻抗 intrinsic impedance。这两个东西的概念很像， 但它们不一样哈。Intrinsic impedance 的基本物理意涵是在材料中传播的电磁波，它的电场跟磁场大小的比值。而特性阻抗它是在传输线 transmission line 里头传播的电磁波、电磁讯号，它的电压跟电流的比值，所以有一点不一样哈。虽然它代表其实都是电磁场或者是电磁波或者是电磁讯号，它的电场跟磁你都可以想象它是电场跟磁场的比例啦哈，但是其实细节是不太一样的哈。好，那所以要注意到的是the thing that is noted is the unit for the intrinsic impedance is ohm, which is also the unit for resistance. However, intrinsic impedance is not a resistance. It just happens to have the same unit as resistance. For example, the electromagnetic wave propagating in the space is supposed to deliver energy in the form of electric and magnetic field. It's not meant to dissipate its energy as it propagates. 所以电磁波在传播的时候，你可以想象它主要的目的啦，或者在大多数情况底下，电磁波传播的目的是要把能量从这个地方传到远方，比如说从太阳出发的太阳光线，它大部分的能量其实是抵达到外部的哈，在太阳跟地球之间，它会不会有能量消耗？会，但是非常非常非常少的比例，因为在真空的环境底下，其实电池的能量是不会被消耗的。电池能量遇到什么时候会消耗？电池的能量遇到什么时候会消耗？遇到能够产生感应电磁场的时候，会被消耗。我10几年前在念书，不是念书啦，刚到哪里？我第一个任教的学校是元智了哈。那一年刚好遇到教师节，所以那个教务处就很贴心的每个老师送了一个小小的盆栽，然后跟我们讲说，然后上面还插了一个小卡片，说，你可以把我这个小盆栽摆在你的电脑旁边，它可以帮忙吸收电磁波。然后我就跟隔壁的也是电波领域的老师互相看了一眼，大家笑一笑人家是一片好心啊，对不对他讲的也没错啦，那个植物的确可以吸收电磁波，但你也可以吸收电磁波，我也可以吸收电磁波，我们吸收的电磁波比那个小植物吸收的多得多了简单讲啦，电磁波怕水那为什么？因为电磁波的电磁场会让水分子的那个氢氧键产生振动特别是频率对的时候所以你知道你的微波炉用的频率是多少吗？微波炉用的频率是2.4 GHz 跟那个 WiFi 差不多跟 WiFi 一样。但实际上微波炉也没有说你一定要用2.4啦，只是现在大家都用2.4就用2.4了吧。其实大概从1 GHz 到10 GHz 效果都差不多，都可以那原因就是这一个频段的电磁波可以带动那个氢氧键振荡所以当这一个频段的电磁波打到生物组织啦就是带氢氧键的组织比如说你在 7 买的食品食物里头啦，或者是饮料啦，或者水里头它们就会被微波炉里头的电磁场去加热因为它的能量可以转移到这个食物中的氢氧键而去振动所以基本上电磁波遇到水就要遇到含水分子的材料，它的能量会被消耗掉，以感应电流的形式消耗掉了我又扯到这里来了 对啊，扯远了，我看我还是回去讲英文好了，免得拖太慢。OK 哈。All right, so the intrinsic impedance, the significance of the intrinsic impedance is not a resistance. So because you can think of in general, in principle, the propagating wave is delivering the energy from one place to another. It's not supposed to attenuate or dissipate its energy as it propagates. Otherwise, the wave energy shall not propagate to a long distance. All right. So, so the intrinsic impedance simply stands for the ratio of the electrical field intensity over magnetic field intensity. So it's the ratio of E and H field. However, because the units for electrical field is what? Is voltage per meter. And the units for magnetic field is ampere per meter. So when you divide E with H, you end up with V over A, which is ohm. So it happens to take the unit of resistance, but it does not stand for a resistor. So be very careful about this physical interpretation, all right? And so here we have the general formation for electric and magnetic field intensity, the general solution type. So as you can see, electrical field is in the form of AF plus BG, while the magnetic field is in the form of 1 over eta, 1 over intrinsic impedance. And the rest is AF minus BG. So if you divide it, so for this slide, you see there is both the E and H field is composed of AF and BG. So this stands for the positive going component, and this stands for the negative going component. So if you divide E plus stands for the positive Z component, you end up with what? You have the same AF, but here comes eta, the intrinsic impedance. Again, this is the ratio of E field intensity over H field intensity. If you divide E minus over H minus, you end up with minus of eta, all right? So the ratio, the ratio of the magnitude of the ratio is still eta, the intrinsic impedance for the negative going components. And again, when you can notice that the square root of mu times epsilon is replaced by 1 over Vp. That is the velocity of propagation, for the electric field and magnetic field. All right, so once we understand the general solution for the electromagnetic wave, we can further ask the specific solution for the electromagnetic wave. That is, for a corresponding propagating environment, we of course would like to know the exact solution, including the parameter, unknown parameter A and F in the general solution. Okay, so we will need to substitute with the so-called forcing function or the boundary condition to solve for the specific solution. Okay, and of course we will begin with the general solution as we have on the blackboard. And considering our problem scenario, okay, on Tuesday we have discussed, supposed that for this problem we have an infinitely large current sheet placing in the middle of the classroom. And the current is going up and down in the middle of the classroom. And suppose you are not here, the chairs are not here, the seating and the floor are not here, so it's just a free space with a current sheet in the middle. What happens? The electromagnetic wave produced by this current sheet will go into this direction and the other direction. And because there are no other boundaries, no walls, no ceilings, no floor, the wave, electromagnetic wave, will keep going and going and going. Right? Okay? Then we can assume that there is only one component in one half of the space. So for this part, you will only have electromagnetic wave going to this direction. And in that part, you will only have wave components that go into that direction. So it has only one component in one space because there is no boundary. If there is a wall on that end, some of the electromagnetic wave may get reflected. That will complicate the scenario, but for the meantime, let's assume the environment is relatively simple. It has only the current sheet, the source, and the environment has no boundary. So based on this assumption, we can say that the solution originally is AF plus BG, but because we only have the current source and there are no boundary on its side, so there is only one component on one side. So for the region of z greater than 0, you only have the positive z going components, and for the region z smaller than 0, you have only the negative going component. So for the electrical field, you have AF for z greater than 0 and BG for z smaller than 0. All right? And so you can write up the solution for the magnetic field. So for z greater than 0, you have AF over eta. And for z smaller than 0, you have minus BG over eta. Okay? However, we still need to determine what is A, what is B, what is F, and what is G, right? We still have unknown to solve. So the next thing is to apply Maxwell equation to help us to solve the constant A, B, as well as F and G. So here, let's see what. So let's begin with Faraday's law, okay? So in the following slide, we will use the Faraday's law and the Ampere's-Kirchhoff law, that is the first two equations of the Maxwell equation, to help us to determine A and B for the electric and magnetic field intensity. So to do that, suppose we have a small rectangular region centered at the current sheet. That is, we assume there is a current sheet in the middle of the classroom, right? And we can place a rectangular region that happens to be that happens to get across the current sheet. Now, so the currents flow in the middle, right? And what the Faraday's law says? Faraday's law says what? Okay, over there. It says the closed loop integral of an electrical field intensity equals to what? Equals to the negative of the magnetic flux enclosed by this rectangular region. All right? And the trick we will apply is you kind of shrink the width of the rectangular region. So the width is so small, you only have 2 lines get across the middle, get across the current sheet. Why do we do that? Because what? like this. Well, originally, the closed loop integral on E involves 4 line integral. A, B, B, C, C, D, and DA. What happens if B, C, and DA become smaller and smaller? Well, when it becomes smaller and smaller, the significance is less and less, becomes less, and then it's so narrow that we don't even have to account for it. So now it's so small so that we don't have to considering about it. So the closed loop integral only involves the line integral on AB and the line integral on CD, right? And the line integral AB involves what? Involves the line integral of electrical field over the length, over the path from A to B. So that will be Ex at Z equal to Z sub Z plus. Do you know what is the implication of this subscript? 这个下标代表什么？这个下标代表说，我们把那个长条形的线积分路径，把它缩得很窄很窄的时候，你的那个电场的积分，电场沿着 AB 线段的积分，那个位置几乎已经贴到 z 等于0了，但是你还是在稍微大于0的位置去积分它，所以这个 z 等于 0 plus 指的是它积分的位置是大于0的，但几乎等于0了，就在那个边边而已。而相对的 CD 线段的积分呢？我这边其实写不对了，应该写 DC 嘛 ，A B C D 才对，不应该写 DC， 应该写 CD 才对。因为那个负号这个负号怎么来的？这个负号是那个方向的相反有没有看到？这个是往上走的，这个是往下走的，所以这个其实是往正 x 方向，这个是往负 x 方向的积分。而这个地方的积分的值是什么 ？Ex at z equal to 0 minus， 这边不是很清楚但你应该知道它的意思吧就是说这个电场，这个 Ex 电场，我们取在哪里？取在 z 比0小1咪的地方，很近那为什么要这样做呢？当然其实是为了让我们的答案变得简单一点了为什么？因为那个法拉利定律的等号右边是什么？等号右边是磁通量密度 B 的面积分，也就是那个长条形的面积。但是我们在这边动了手脚，对不对？我们动的手脚说，我把这个长条压扁，所以那个长条的面积其实是怎样的？其实是趋于0的。所以从那个长条形中间有没有磁通量穿过？有。那个 B 不等于0这个 magnetic flux 并不等于0，但是因为它要积分的那个面积被压得很小了，所以它的效果等于0所以我们这边玩的这一个招数就是法拉利定律里头等号右边，因为那个 B 的面积分，因为那个长条形趋于没有宽度，宽度几乎为0，所以那个地方就变0，就变成封闭回路线积分等于0。The closed loop integral on electrical field intensity equals to 0 as we squeeze the width of the rectangular region approaches to 0. Therefore, we have the result is AF, because the lengths of A, B, and CD are the same, so they can be cancelled. The lengths of the two vertical line are the same, So they can cancel each other, and it becomes AF minus BG equal to 0. So you can write up as AF equals to BG. And this thing is satisfied only at Z equal to 0. Okay? Now, this relationship is only satisfied at the position around at the source. That is Z equal to 0. So since AF equal to BG, the A and B can be the same thing, and we can substitute AF and BG with function F, as shown here. As shown here. So as you can see, when Z equal to 0, the solution at the two sides are both F or function T, or a function on both sides. However, as the observation points move away from Z equal to 0, this becomes T minus and plus Z over Vp. It takes the form of a general solution for the function parameter. All right. So using the Faraday's law, we understand that the AF and the BG are the same, at least the same at Z equal to 0. And so we can have the formulation for the magnetic field intensity H. It becomes positive and negative of 1 over eta times F function. Okay? So we have this based on the Faraday's law, we know that AF equals to BG and equals to F at Z equal to 0. At Z equal to 0. Okay? And based on this result, we can we can simplify the general solution for E and H as these two functions. However, we may argue that what is function F? Right? What is function F? This is still an unknown. So what should we do next? Again, we ask for help from Maxwell equation. Right? We already used the Faraday's law. However, we still got another tool. We have Ampere-Sakisho law. Okay, so we write out the Ampere-Sakisho law, that is this thing. Del Hy over del Z equals to Jx plus del D over del T. Or you can have it in integral form. That is the closed loop integral of H over a specific path equals to J ds plus right? Okay. And note that electrical field is vibrating on the x direction, and the magnetic field is vibrating on the y direction. So the closed loop integral should be performed on the y direction. So here we have another rectangular region that is placed in the middle, that is Z equal to 0, but it's placed horizontally. So as you can see here, there are electrical current J goes to get across the rectangular region, right? And we are trying to evaluate the closed loop integral of the magnetic field intensity on this rectangular path, right? And again, we will do the same trick as squeezing the width of this rectangular region. So we only have to account for the line integral of H along EF, past EF, and the line integral of H along past GH, which on Z at 0 plus, and the position Z equals to 0 minus, right? So the closed loop integral is reduced to two line integral at Z equal to 0, at a 0 plus and 0 minus. So here we have EF times HY at a Z equal to 0 plus. And HG, the line distance, the path distance, the path length times HY at a Z equal to 0 minus. And what is the result on the other side? The other side shall include the surface integral of electrical current density and the time derivative of the surface integral of displacement flux d. And because d is distributed evenly distributed across this rectangular region, and because we do the trick of reducing the width of the rectangular region to approximately 0, so the second term can be neglected. The product of d times the surface area approaches to 0, as we see in the previous example. On the other hand, the current density J is still there. It's a surface current density. So no matter how small the rectangular region is, how narrow the rectangular region becomes, the current density is still there. So the surface integral of J can be reduced to the width of the rectangular region times the surface current density J. And the width happens to be what? Happens to be the length of the rectangular region, EF and GH. All right. So we have a non-zero result on the right-hand side, and it corresponds to the difference of magnetic field on the two sides of the current sheet. So you have EFHY at Z equal to 0 plus minus HG times HY at 0 equals to 0 minus equals to EF, the width of the length of the rectangular region, times the surface current density, JS. Okay, so this is non-zero. This is non-zero. And so here we have a result that is based on the previous assumption that HY is F over eta 0. So the left-hand side becomes 2 over eta 0 times Ft equals to JST. That is the surface current density on the current sheet. Therefore, the unknown F function can be solved as eta sub 0 over 2 times Js. So the F function is proportional to the surface current density Js. And substitute F function with eta over 2 times Js, we have this solution. That is, the electrical field intensity becomes eta over 2 times Js, which is a function of parameter T minus and plus Z over Vp. So, and the electrical field is vibrating on the x direction. The magnetic field H is vibrating on the y direction. 这边少了一个 P Vp 自己补上去. And for the magnetic field, it becomes plus and minus 2 over 1 over 2 times Js. So you can see the electrical field is stronger than the magnetic field by a factor of eta sub 0. And you have a plus and minus sign across z equal to 0. So they are the solution for z greater than 0 and z smaller than 0. Okay? So here is the solution for the specific solution for the electromagnetic wave for an infinite current sheet. And then the result shows that the electrical field variation is totally determined by the variation of the electrical current source, the J function. And for this case, J function is represented with minus Js, a function of t, at the x direction for z equals to 0. And the solution from deriving this in this line becomes the so-called uniform plane wave. And they are propagating on positive z and negative z direction. So the electromagnetic wave is produced by time-varying electrical current. They are and the wave are propagating on both sides of the current sheet. And the time variation of electrical field component Ex in a given position z is the same as the current density variation delayed by the time z over Vp and multiply by eta sub 0 over 2. Okay, so let's discuss a little bit about the solution. Take another look at this solution. Why there is a factor 2 over here? Well, you can simply recognize as because the current sheet is situated in an environment without boundary. So half of the energy propagate to the positive z direction and half of the energy propagate to the minus z direction. So we can imagine that the fact 2 stands for that half of the power, half of the electromagnetic wave energy goes to the positive z and the other half goes to the minus negative z direction. Right? So if you combine the two, it becomes 1. Because the energy is propagating in the free space. So half of it goes to positive z and the other half goes to negative z. And how about the significance of this part? This part stands for the time delay. So as you know, if the sun vanishes at this very moment, when can we feel about it? About 8 minutes later. If the sun is removed by the alien now, then we will feel it 8 minutes later. So there is a time delay. Another example is that we are looking at your lecture, that is Professor Liao in the front of the blackboard. But are you looking at me, the present me? 你看到的我是现在的我吗？OK， 我看到同学在摇头，很好你已经猜到我的答案了。你看到我是什么时候的我？一小段时间之前的我比如说你同学坐在我最前面吧，你看到我大概是20个 nanosecond 之前的我吧，为什么？因为光跑的速度是1秒是3乘以10的8次方嘛，所以1个 nanosecond 是多少？0.3公尺。所以光跑的时间是1个 nanosecond 30公分。所以根据你现在跟我坐的远近，你看到的我大概是10到40个 nanosecond 之前的我。所以假如现在突然司法消失的话，你要大概40个 nanosecond 之后才会察觉到，老师不见了OK。所以在那个方程里头，你看到的那个 t 减加 z over vp 代表的是什么？代表的是电磁场发生的电磁波发生的位置 到你观察者位置的 time delay 时间延迟，所以这一点很要紧哦，就是同学在学电磁波的时候，你要留意到的一个现象，就是说电磁波的传播是需要时间的，所以你观察到的时间其实都是在某个 time delay 之后所产生的电磁现象。这一点跟电路学非常的不一样。电路学你可以假设说，你的受质发生讯号的变化，或者电路的开关发生变动，电路上面的其他位置马上就可以察觉到。但是在电磁学里头，某个地方的状态产生改变，它是需要一段时间才会被电路上面的其他地方感受到，所以要去留意这一个时间延迟的问题。好，我们先休息一下。Okay, so let's continue for example 3.10. So in this example, we have let's consider a current function JST. So the plot below shows the variation of the current function Js, which is it's like somewhat like a step function. So we first check the horizontal axis of the plot, that is the time axis. And the vertical axis is the magnitude of the current, that is the Js, the surface current density. So as you can see, at the time, starting from time equals to 0, the current density grows a little bit linearly. The current density grows linearly from 0 to 0.1 amp at t equals to 1 microsecond, 1 microsecond. And then the current density will hold as 0.1 amp until t equals to 2 microseconds. Then above t equals to 2 microseconds, the current density vanishes and the d is reduced to 0. So the current density, the currents only appears between t equals 0 to 2 microseconds, and the maximum of the current density is 0.1 amp. So according to this current variation in time, which is located at z equal to 0, the example, the question asks you to draw the solution for Ex at z equals to 300 meter. That is, if you locate it at z equal to 300 meter, what is the electrical field intensity variation versus time at this position? And you are asked to find the variation, the time domain variation. Here is Hy versus T, the time domain variation of the magnetic field intensity at z equals to minus 450 meter. So question A and B ask you to draw the time variation at a different position of electric and magnetic field. And problem C and D ask you to draw the spatial variation of the electric and magnetic field intensity at t equals to 1 and 2.5 microsecond. So part C and part D asks you to draw ES and HY versus Z. So that is the spatial variation. 所以注意到这个 A、B、C、D 问题的差别，A、B 要你画的是时域的变动，在特定位置上面的电场跟磁场的时域变动，而 C、D 呢，则是问你在特定时间点，比如说1个 microsecond 跟2.5个 microsecond 的时候，它在附近空间的电场跟磁场的空间变化所以 A、B 问的是时域变化 ，C、D 问的是空间的变动。那当然你要搞清楚的是这个电流的function它的变动， 特别是它出现的先后次序，哪边先出现 ？A、B 先出现嘛，然后 C、D、E 结束，然后它只出现2个 microsecond 在真实情况下，当然比较不太可能出现这样的电流变化，但是没关系呢，我们现在只是做一个概念的一个澄清跟熟悉哈。So here are the solution. So let's look at the solution one by one. For part A, because the wave velocity, the electromagnetic wave propagating velocity Vp equals to c, that is 3 times 10 to the eighth. So it corresponding to time delay of 0.3 meter for every nanosecond, and it's equals to 300 meter for every microsecond, which means the wave, the electromagnetic wave, shall propagate 300 meter for each microsecond time delay. So for this case, you are asked to draw the electrical field variation in time at the position of z equal to 300 meter. So because the distance to the source is 300 meter, you will only observe the electrical field at t equal to 1 microsecond, which is corresponding to the propagation delay. And because the electrical field solution for electrical field intensity is this, that is eta. What is eta? Okay, in the previous slide we already seen that eta equals to 377 377欧姆这是free space 的本质阻抗 intrinsic impedance for free space is 377 ohm, which is determined by mu sub 0 and epsilon sub 0. And because of that, because electrical field intensity equals to 377 divided by 2 times the function for the electrical current, so that will be 188.5 times the magnitude of Js. And here is the magnitude of Js is reached is maximum at t equal to 1 microsecond, and the magnitude of the Js is 0.1. So the maximum for the electrical field intensity observed at z equal to 300. So be careful about how you draw the horizontal axis and the vertical axis. The horizontal axis is the time variation. So you only observe the field starting at 1 microsecond. And the field stops at 3 microsecond because the source vanishes at 2 microsecond, and consider that there is 1 microsecond of propagation delay. So your electrical field is observed between 1 to 3 microsecond. And as to the magnitude, that is the Ex at the z equal to 300 meters. So to be sure to mark this in your final questions, right? Oh. 因为这类题目比较好改嘛，对不对？一翻两瞪眼嘛，所以我会喜欢这一类的题目嘛，所以你要是啥都没画，那就会划掉了嘛。OK， So as to the magnitude, that is what? 188.5 divided by 10. So the maximum value you can observe from this is 18.85. Right? And let's move on to part B. And because the position, observing position is 450, so it takes 1.5 microsecond for the wave to reach at your observation point. So the time delay is 1.5 microsecond. And because the position is z equal to minus 450 meter, so the solution you adopt is actually h equals to minus 1 over 2 times JS function, and it's in the y direction. So as you can see, the results shown here is the horizontal axis is time, and you only observe the signal starting from 1.5 microsecond to 3.5 microsecond due to the presence of the JS variation. And as to the magnitude of HY, here comes with a minus sign because you are located in the Z smaller than 0 region. And because this constant over here is minus 1 over 2. So the maximum you observe is minus 0.5 ampere per meter. So it's the maximum magnitude you observe is 0.05. It's 0.05. Okay, it's 0.05. That is its position. And as to part C, you are asked to sketch EX versus Z. That is the spatial variation for a fixed time value. And the time specified is T1 is 0.5 microsecond, which means that only part of the current signal is shown, because you are asked, sorry, 1个 microsecond. So the time specified is 1 microsecond. So only half of the signal emerges. So only the part from point A to point C emerge from the source. And corresponding time delay from point A is 300 meter. It's one microsecond. It's 300 meter. And so as you can see from this plot, the horizontal axis is Z. So you are asked to draw the spatial variation. So you can see for the electrical field, which is an even function on the two sides of Z equal to 0. So the signal, the electrical field signal emerges from Z equal to 0 and propagates to positive and negative Z direction. And the tip of the signal reaches up to 300 meter on both sides. And the maximum of the electrical field intensity is 18.85 due to the magnitude of the JS, which is 0.1. And so here is the solution for part C of the problem. As to the part B of the problem is the draw sketch for HY at t equals to 2.5 microseconds. And because the current signal appears only between 0 to 2 microseconds, so we know that the current signal is fully appear in this time instant. And in fact, the front of the signal reach all the way up to 750 meter. And to the end of the signal already reaches up to 150 meter for this case. So here is the sketch of the magnetic field intensity. Horizontal axis z-axis again, and the vertical axis is the HY function. HY, the magnetic field intensity at t equals to 2.5 microsecond. 2.5 microsecond. And the magnitude is positive and negative because, as we've seen from the general solution or the specific solution, the sign of the magnetic field intensity are different on Z's greater and smaller than 0. And the maximum magnitude is 0.05 amp. So you can draw the variation in magnetic field intensity according to the specified current function. So you have different sign across z equal to 0, and the the function due to the emergence of the electrical current is fully observed across this region. So be sure to look at this problem again at home.